Welcome back to AFX360. I think it's safe to say that our two speakers coming up are two veterans in using AFX and using beam shaping for powder bed fusion. So it's my pleasure first to introduce Richard Rothfelder from the LPT in Erlangen. He's in his 4th year of his PhD thesis. He's very experienced in processing especially titanium in powder bed fusion, and he's going to show a very special method on how to quantify and visualize spatter in processing titanium. So Richard, stage is yours. We're happy to have you.
Thank you very much, Andreas, for the kind introduction. Thank you. I'm very happy to be here today and be able to present us our results on the spatter formation, especially the spatter formation and dependency of a beam shape. I'm part of the Collaborative Research Center, CRC 814. We have also a booth when you want to see a little bit more about our work, because I will go to a little bit about into detail why we are using the beam shape in this specific context. So, first of all, we have a short overview of a PBF machine in general. We have our build area, we have our powder reservoir from where we get our powder material. I think most of the people who will be here today will already know this, so I won't go too much into detail about the mechanical parts. But the standard right now which we are using is a Gaussian beam distribution, which is emitted by most laser sources. But nLight, with their AFX system, gave us a very easy way to change the intensity distribution and the beam shape in the process itself. And we will discuss a little bit about the challenges and opportunities linked to the beam shaping itself. Today, the topic, as you may guess from the title, will be, I will talk about the spatter formation, independency of the beam shape, because there's a huge influence when you compare Gaussian beam to the ring point profile. The state of the art of the PBF-LBM process, we have our process parameters which define our specific process, where we have laser power, scanning speed, hedge, and layer thickness, which is not that common anymore, but those are the 4 main parameters you normally talk about when talking about powder bed fusion. Then we have our material, which gives us the optical properties, thermal conductivity, phase transformation, microstructure. So for the optical properties, what are we talking about? Reflectivity, the absorption, for example, copper. When you work with a normal infrared source, then you have a very high risk of damaging your optics by back reflection, which then, for example, is already reduced by a ring shape. The thermal conductivity, there we have an interesting effect, how specific alloys react to the beam shaping. For example, due to its very low thermal conductivity, Ti64 reacts completely different to a beam shape than LC10 Mg, for example, would do. But now we come to the beam shaping, where we get way new possibilities considering our process development and how to produce parts. Because the geometry of the beam shape is, we have several different approaches. The easiest way, or which already is in use, is just defocusing your Gaussian beam profile, which is already a kind of beam shaping, so to speak. But with the new approaches like the system from nLight or C1 or DOE spatial light modulators, you could get nearly any shape you want. And then again, when you have your shape, there's a point of the intensity distribution, like for example from the AFX, where you can shift the power from the center to the ring, always creating different results at my powder bed. And then the static dynamic. This is a whole new topic, and the focus today will be on the static beam shape, where we talk just this ring shape you see down here will be the beam shape the material itself sees, so to speak. I will show you a little bit video footage about what is possible with dynamic beam shaping, but this is more of an outlook. So, beam shaping. When I talked about the geometry, I will show you now 2 different beam shapes, the rectangular one and the rhombus-shaped one. And why are we interested in the beam shape? Why it defines our melt pool on really the highest level of control we will get. And now I will show you what happens when I use the rhombus shape, for example. You really see we have straight edges. So this is really a rhombus-shaped melt pool. considering hot cracking, for example, this wouldn't be the best opportunity, so to speak, because there are more round shape would be preferable. But on the other side, where we see the rectangular beam shape, you really see we have a complete straight front. So by beam shaping, we have the possibility to get control over our melt pool, which is the most important part of the powder bed fusion system, because it defines the addition of more different melt pools creates the line, and the line is then again the unit self of our parts. But there we see it really does matter how our shape looks like. When we have a ring, we will have a ring-shaped melt pool. When we have a rhombus shape, we have a rhombus-shaped, rectangular, so on. We get this is, as I told you already, this is very important when considering hot cracking. So you can, by changing the intensity distribution and geometry of your shape, avoid hot cracking. With parameters, you normally would get hot cracks in, like, aluminum 2000 or 6000 alloys. Just with the same parameter set, using a different beam shape could already avoid the hot cracks completely. Then again, I told you about the possibilities of dynamic beam shaping. You see, this is what we called the Wi-Fi beam shape, which is directed as you see here. And both lines I will now show you have the same profile and the same parameters, 1 meter per second, 1 kilowatt. And the only thing that changes is the intensity distribution over time. And you will see what happens when we just have a very high frequency, which is then again the same situation like we could talk in the AFX system. You really have a smooth, round melt pool, which would be really good for working in additive manufacturing and a powder bed. But now we could change the frequency of our profile to create another effect. And I told you it's completely the same. Just the temporal intensity distribution alters. And then we get a complete different result where we can control the flow of our melt to the millimeter. We have a repetition, choose the repetition time so that these curves are driven in 1 millimeter steps, and when we measure it, it is 1 millimeter to the micron. So we have an extreme degree of control via the temporal adjustment of beam shaping. For example, the AFX system itself has the possibility to change between the beam shapes. So when you have an advanced monitoring system for your weld tracks, you can just switch the beam profile to a one which would get perhaps broader to compensate for a little lack of fusion or pores on the surface in the previous layer, for example. But good, this was our short excuse to dynamic beam shaping. Now we go for state-of-the-art in the area of beam shaping, where most of the literature works with the melt pool level, so the influence on microstructure, where we have a lot of work in the USA. It is very interesting but this is a basic research step approach. Here is often discussed what does the solidification look like, what is the resulting material in my weld track. But this is again on the melt pool level. It's hard to scale this information up to a complete part because you remelt mostly every volume element of a part several times. So it's not just enough to simulate one single track. You have to take into account the geometry of the part and the overlap of all the weld tracks over time. Then you can work on specific problems like the decrease in hot cracking the hot cracking risk in your alloys, or in my case where we want to try local in-situ modification, meaning that we drop smallest amounts of powder into a powder bed, and then we want to avoid that the spatter formation carries away most of the powder we put in there. Then on the component level, which is, I think, for the application, the most interesting part is where we talk about the potential for build rate. She and Röhling, for example, work on the influence on the microstructure. My former colleague, Michael Rasch, worked on the hot cracking risk, especially in Wirschop and Grünewald, have a very interesting publication on the potential for build rate, but they also disagree on some points, so there's still work to do. Our motivation, as I already told you, I am a member of the CRC 814 in the subproject B5, where our scientific objective is to understand the interactions while we are forming additively manufactured parts or hybrid components under the influence of a local in-situ alloy modification. Like I told you, we just won't build up a part of complete Ti64, but locally we will use an adapted, better stabilized alloy, which is way better formable. With steel, this already works. There's not a problem, but steel is very good formable in comparison to Ti64. With some local modifications, we could make this possible that we build these hybrid components also of Ti64. And well, I'm working together with the colleagues of the Institute of Manufacturing Technology. They work on the forming operations. My part is the local in-situ alloying in the PBF-LB. And this will also be the focus of today's talk. A little bit about the theory of the local in-situ alloying. We will build just little elements on our substrate plate, and the deformed substrate plate after this will be our hybrid component. But as you know, normally I have just one feedstock, so just one single powder I can work with in the powder bed. Therefore, we want to locally increase the formability of our Ti64 part and preserve its mechanical properties on the surface. So like you see here, I'll have the modified soft alloy in this area and the Ti64 on the surface where I want the high mechanical strength. We stabilize the better phase by dropping very little amounts of iron and vanadium into the powder bed via a robotic arm system, removing this from the place, scanning the area, and then we coat again. So it's just more of an interruption between the coating steps to get this local in-situ modification. The challenge is here that the spatter formation and the resulting feedstock contamination right now wouldn't, it's not good for your application, because when you have a lot of powder and contaminate it with, for example, you want Ti64, but then you got iron and vanadium in it, which completely changes the mechanical properties of your alloy. You want to avoid that, and therefore we have to drastically decrease the spatter formation, which moves the particles around the powder bed surface in the first place. So our research question is if it's possible to reduce our spatter formation in the distributional build area in comparison to a Gaussian beam by using beam shaping. In this special case, the AFX laser system. The characterization of spatter formation itself is challenging. Normally, we do it via high-speed imaging of the process zone, which allows a quantitative determination how much spatter do leave the process zone, but you don't know where they land. And they can create void defects, but it's hard to say from where does this specific one originated. So it's hard to get any information of your process strategy considering your defects. When the distribution of spatters on the powder bed surface is only estimated approximately, and when their spatters land on the surface, they will be completely molten, so we won't be able to find them anyway later on when we do a normal analysis by cross-section. How do we tackle this challenge? Now we see here our Ti64 base powder. We drop in the vanadium and iron mixture. Then we start. This would be the way it normally would be. We're in the area where we don't have the mixture. We have our base Ti64 and our better stabilized alloy in the area where we have the mixture. But now this spatter formation would just land anywhere, and we wouldn't be able to find it because it just would go into solution and build a new alloy. But it's very hard to trace very little amounts of vanadium or iron in your, then again, mixed powder with the titanium. So we added tungsten particles. Why tungsten? Tungsten is extremely dense, so we won't melt and has an extremely high melting temperature. So with the parameters we use for Ti64 and the base alloy, we will not melt it completely, so it won't get into any kind of alloy. It will more form a metal matrix composite. And when it lands on the surface, even on another part, we will be able by cross-section just to count the amount of spatter particles we find there. So this is the working hypothesis. I took a little bit in advance. One can quantitatively qualify the spatter formation and the distribution on the build plate by using tungsten as tracer particles. Here you see now our experimental setup. This is in the middle what we built up here. We had squares on a substrate plate from an SLM280 integrated with the AFX laser system. We have the length of the sides is always 50 millimeters. We build up 50 millimeters. Then in this area, these cutouts, we place tungsten powder, then scan again the whole area to move the tungsten. And afterwards, by the cross sections, we will be able to find these tungsten particles and check independency of our used beam shapes, the Gaussian beam and the ring point beam profile, which creates the most spatter, and how far do the spatter travel during the scanning process. Our laser parameters were for both cases 400 watts, 900 millimeter per second scanning speed, a hedge of 120 micron, and a layer thickness of 50 micron. So pretty standard. Now you see how this looked then in the end. As I told you, we built up to this to a height of 5 millimeters. Then we placed a pinhole on the surface, removed the Ti64 powder, and placed in every disc cutouts a defined mass of tungsten to be sure that it's not just the mass of tungsten which leads to different results here. And we are always 3 grams of tungsten, so we had the repeatability made sure. Now we come straight to the results and discussion. So first of all, we had to check our approach and show that the particles we found in the grinded surface are really our tungsten particles. And we checked with the EDX measurement, and it showed, yeah, we do have really tungsten particles. They are the correct size. They are the particle size distribution from our tungsten powder in the first place, which is quite interesting. You see these smears, which is tungsten that goes into solution a little bit. It's more interesting when you consider matrix metal composites, because, for example, in steel, when you use tungsten as hard particles, they normally get a very crack, risky area around the particles. But this tungsten particles goes a little bit into solution with the matrix and therefore creates a really strong bond, which could be interesting in the future. But this is just an idea beside the main topic. We showed that we really have tungsten in the surface. And afterwards, we grinded the specimens from the different locations. As you remember, we checked those 3 especially to compare how much 2, 4, and 7, how much tracer particles can we find on the surface in dependency of our beam shape. And it showed to make it a little bit more easy and understandable, we just scanned with a microscope the surface, and then in every place where we found a tungsten particle, we made a mark with an identical amount of, every time an identical amount of pixels, and then just compared the amount of pixels, where around 50 pixels equals 1 found tracer particle. But here we really see a strong difference. When you see on the Gaussian area, we have particles everywhere over the place, with where we normed it to 100% with this 1.5 million pixels for the Gaussian beam distribution. And in comparison, when we look at the ring shape beam profile, we see that this dropped to nearly 21% of this. So we have an extreme reduction of our spatter formation, which was already shown with high-speed imaging on the process zone itself, but we never saw it on the build plate or the part itself, which we see now here. And when we compared it to the rest, we really have a mean reduction of our tracer particles by 75% when we're using the ring point shaped profile. So we have a significant reduction of feedstock contamination due to beam shaping. In the meantime, we double-checked our results because, okay, this was just on the surface and maybe we were missing some parts. But there again, tracer particles prove very valuable as tungsten particles prove very valuable as tracer particles because they are extremely dense, and therefore we are able to detect them via a micro-CT scan. There I have to thank my colleague Benjamin Baumgärtner from the FMT, colleague from the CRC also. And here we see the same results. On the left side, we have an extreme amount of distributed particles over the complete area where we used our Gaussian beam. It's also not on the surface, but also in the volume. And when we look at the right side, there we nearly have no particles at all in the complete surface. And the only mass of particles is the area where the coater shoves them to this area and where the laser just sinter them together. But this is even more than 75%. This goes more to 95%, but we didn't do this comparison in all the specimens, so we stick with the 75% in the mean, but you see it's also even more. And therefore follows our summary. Our experimental results allow the quantitative evaluation of the spatter formation and dependency of the beam shape by using tungsten as tracer particles. And the tracer particles distribution of the ring point profile shows a significant reduction in the deviation in comparison to the Gaussian beam profile by 75% in the mean. And the use of the ring point profile is a very promising way to reduce feedstock contamination. In our special case, where we want a local in-situ alloying, but less spatter won't be a problem for any powder bed process itself. And then a short outlook what we will do with these results in the future. We will use the ring point profile for further process development during the local in-situ alloying, where we will go for higher layer thicknesses than are normally processed in the additive in the powder bed fusion. We went up to 250 to be precise, to go around that when we drop the powder on the surface, we have a little hills, and therefore we need parameters which are able to compensate higher layer thicknesses. But in combination with the ring profile, we already did some work there, which will be hopefully published in a few weeks. This is where we go to also the investigation of the possible increase in build rate, which were normally done for aluminum alloys, but we haven't one for Ti64. So this is really also very interesting if we can reproduce them without regard of the material. And the influence of the beam shaping in the dispersion of the additional alloying elements in the bulk material will be very interesting, where we look how far do our additional alloys travel in the solidified part when we compare a Gaussian to a ring-shaped beam. And the analysis of microstructure mechanical properties of in-situ alloyed parts for our material model, where we then will simulate the necessary strength of the forming operation to finish the complete idea of B5. But this is the end of my talk. Thank you very much for your attention and would be happy to answer any questions.